speaker tonight is Dr. Jere Lipps. As you can see, he's as I can, and he is the director of the Cooper Center. He's been there a year and a half now, something of that nature. After a long and distinguished career elsewhere, mostly at the University of California, Berkeley, a university which I highly recommend, being my alma mater. He was a professor of paleontology and integrated biology. He was also chair of the Department of Integrated Biology. I have to read this. There's so much material, but I'm not going to read all evening. But I could. There's that much material. The career has truly been distinguished. And he was the director of the curator of the Museum of Paleontology and the chair of the Berkeley Natural History Museum. So he has a good background in museums. His particular field of interest is the ecology and paleontology of marine microorganisms, animals, and marine animals. Throughout the course of 30 years, he's conducted field research in Antarctica, French Polynesia, Papua New Guinea, New Zealand, Australia, Galapagos, and North America's West Coast. And I think I travel a lot, but except for North America's West Coast, I have not been to any of those, so he's covered a different part of the world than I am. His interest, he's largely interested in processes rather than particular organisms. Much of his work has dealt with extinctions, sea level changes, both related to global warming and cooling, the topic of tonight's talk. I think the most interesting thing in the whole curriculum vitae and his background is that he has an island in Antarctica named after him, in honor of the research that he has done there. So, again, a distinguished career, I would say.
Thank you very much. You very nicely condensed all that material. I'm interested in climate change now because I've been studying the fossil record of climate change for most of my career. I've been interested in the changes of environments through time and how those have affected organisms, both in terms of their extinction dynamics and in terms of their evolutionary radiations. And this has been a career essentially started right here in Orange County at Newport Mesa. When I first got interested in paleontology, there used to be, underneath all those houses, still are, shell beds of Pleistocene material about 125,000 years old that represented an old stand of sea level. So the first thing I ever did was to get involved with sea levels. And later on discovered that there are many things that control that, and climate is very important. So I want to review for you briefly some of the factors that we'll be talking about tonight. And so what's the problem? We all know what the problem is, but there are different takes on it. I'm going to take a strictly scientific view of this based on the facts that I see and read from the paleoclimate record, which is very complete, from the historical record, and then we may try to use modeling to project that information into the future. But these are different strategies. So the first two have lots of complexities to them, the paleoclimate record and what's going on today and in the recent historical past. That's just factual stuff. The models are based on the way people interpret things through their computers and what that might mean for the future of humankind. So nature does play a role in all of this. In fact, you'll see in a moment that the climate has always been changing on the surface of the Earth. And right now we're at one of the more pleasant times in that history. So nature changes the climate, and we clearly change the climate as well, mainly by the emissions of transportation through the burning of fossil fuels and power plants, but other ways as well. So this is a 66 million year record of temperature fluctuations in the higher latitudes based on organisms found in deep sea cores. So these organisms live on the bottom of the ocean, and so their temperatures reflect where that bottom water is coming from, which is the polar regions most of the time. And you can see that the world has been much warmer most of the time and fluctuating all over the place, so that if you were to magnify each one of these little areas up, you'd see that it's quite fluctuating during those periods of time. But there are big points of high times like this one. At that time, temperature average of the globe was 12 degrees centigrade. Now it's nothing like that. And then it's come down to periods of time like here at about 33 million years ago. And it gets a little bit cooler, comes up, some more peaks in here, and then it begins to really go downhill like that. In fact, there's a complication up in this part of the curve because we now have Antarctic ice being frozen on the continent and ice frozen on the northern hemisphere. And the way the signal works, in order to get this curve, it's based on oxygen isotopes, two different isotopes, oxygen 18 and oxygen 16. And it turns out that when water evaporates from the sea surface, it preferentially takes oxygen 16, therefore the water becomes enriched relative to some standard in oxygen 18. That gets incorporated into the calcium carbonate, CaCO3, the oxygen part of that, gets incorporated in the shells of these microorganisms, and then you can read the temperature. The problem when you have ice there is that you're also reading an ice effect, because now the oxygen 18 is higher than it would have been, say, back here. But we know how to correct for that. So although this curve goes down below zero, it really isn't below zero. It's more up around here. And that is a factor of the ice ages. Antarctic ice started accumulating 35 million years ago on the Antarctic continent, and we have lots of evidence for that. And then the northern hemisphere started about 5 to 6 million years ago. So it's always changing. Let's look just at the last 700 or 800,000 years now. And we can see that we've been going through fluctuations of time and climate, from glacial cycles, low points, to interglacials, high points. And here we are today at temperatures that are around zero today. But this side over here measures sea level. We can reconstruct these curves to sea level because we can relate that to the amount of ice on the continents, and that we can read out of the oxygen isotope record as well. So this is solid science. And this graph then shows us interglacial times. These are the peaks of warmth, and then we're at a peak of warmth today. Most of the time, you'll notice, it's been a lot colder in the last 700,000 or 800,000 years. In fact, the last 2 million years. It's mostly been colder than it is today. The last time we had a interglacial period was 125,000 years ago, and at that time sea level was higher than it is today by 8 meters. Worldwide, 7 or 8 meters. And now it's at what we consider to be the baseline sea level. Now we can also, looking at air that's been captured by ice, as the snow falls in Antarctica, it captures bubbles of air, and that then gets incorporated into the ice cap. And by drilling ice cores through the Antarctic ice sheet at Vostok Station, we get a complete record of both temperature in blue, and by measuring the the CO2 in the bubbles in the ice, we can reconstruct the amount of CO2 in parts per million in those ice bubbles at the same time and with the same samples as we're getting the temperature data. So these two curves go together. And you'll notice that when it gets warm, like here, there's more CO2 in the atmosphere. Same here. When it gets cold, you lose that. And there are biological reasons for that. And also physical reasons. When you warm things up, you release more CO2 into the atmosphere. But notice, here's 300 parts per million over here of CO2. It's never been, except for this one peak, that high before. For 2 million years, it's been around 280 parts per million max. And most of that time, it's been lower than 280 million parts per million. Why is this important? Because CO2 is a greenhouse gas, and the more that's in the atmosphere, the more the atmosphere warms. And we'll go over that in a moment. So this is the curve for the last 125, 150,000 years. Here's that last interglacial, which is 8 meters above what we have today, which is over here. And this is the curve for the climatic curve. You'll notice that there is this carbon dioxide superinterglacial imposed on top of this. That's the problem there of additional carbon dioxide created by humans by burning mostly fossil fuels, but other things as well, that would release CO2. And this slide is one I used when I taught Geology 1 to students in 1970. It's still right on with one major exception. Well, two major exceptions. One, we don't know, at that time we didn't know what this peak would be. But the second one is, you'll notice that it turns over and it goes back as though it's in another ice age. That probably can't happen anymore because we've superseded that small little change that causes those kinds of glacial interglacial cycles that I showed you before for the last 2 million years, and these two. So it may be that we're well on our way back towards a super interglacial or a super greenhouse. So what is global warming? You may know this, but let me see if I can't give you a different take on some of this. The 3 terrestrial planets, we exclude Mercury because it doesn't have an atmosphere. Venus, Earth, and Mars are all greenhouse planets. They all have gases in their atmosphere, CO2 principally. And I'll show you why that's important. And so those certain gases that we call greenhouse gases trap heat in the atmosphere. And these are contributed by natural processes like volcanoes, certain activities of organisms, and human activities, burning chiefly fossil fuels. And it's gotten to the point where nature can't remove it fast enough by dissolving it into the oceans and then having organisms or inorganic processes absorb that CO2 and change it into calcium carbonate. And so the atmosphere is warmed and it's linked to the ocean, and the ocean is the big heat sink. So the ocean keeps a lot of heat, and it also dissolves CO2. Here's the principal greenhouse gases. Water vapor is a big greenhouse gas, but it's so ephemeral in the atmosphere, it really balances itself out to not doing very much. Carbon dioxide is the big one because it's contributed naturally through volcanism on all of those 3 planets that we just saw. And methane, CH4, is a very powerful greenhouse gas. It's 21 or 22 times more powerful in terms of trapping heat than carbon dioxide. So those 2 are the principal ones that we need to worry about. These other ones contribute as well, but carbon dioxide lasts in the atmosphere for hundreds of years, about 300 years. Methane, although it's much more powerful in terms of it trapping heat, only lasts in the atmosphere for maybe 18 months or so. So it cycles back out. So here's the greenhouse planets. The atmosphere of Venus is 90, well, we measure atmospheric pressure in bars. That stands for the pressure at sea level on Earth or the pressure at the surface of these other planets. Venus has a pressure of 90 bars. We have a pressure of 1 bar at sea level. Mars is about 1/100th that of Earth. The atmosphere of Venus is 96% CO2, super greenhouse planet. Mars is also 95% CO2 in its atmosphere. Venus is so hot below that atmosphere that when the Russians landed Venera 1 back in the 70s, it took one picture or two pictures and then it burned up because the temperature of that surface is around 700 degrees. And it's because not only is Venus closer to the sun, but all the heat's being trapped by that CO2 in the atmosphere. It was quite a volcanically active planet as far as we know. Now the difference between Venus and Mars is not so much in the percentage, but in the atmosphere itself. This is a very dense atmosphere. This is not a dense atmosphere. It's 100th that of Earth. This is 90 times more dense than the Earth. So that's much harder. This is much cooler, -60 on the average, on the centigrade, on the average on the surface of Mars. But look at Earth, 0.04%. That's 400 parts per million. Why is that? It's because CO2 recycles into our oceans and gets precipitated out in calcium carbonate and a few other things. So we can recycle our CO2 into the ocean where it's made into the shells of organisms, and those drift over towards the continents as the plates of the ocean subduct underneath the continents. And when it subducts under the continents, then volcanoes are created, and that CO2 is re-released into the atmosphere again. But it takes millions of years for that to happen, hundreds of millions of years. So that's why these planets, although they're all producing CO2 through volcanism, why they differ in their characteristics so much. So let's look at another core at Vostok. This goes back 400,000 years, and this is CO2. And these curves match the temperature curves. Here's the 125,000-year-old peak. It's at about 290 parts per million. Here we are just a little bit more than that. That's the one that's up to about 300. And then they stopped this curve because the ice, you can't do this in the very surface ice because it's just fluffy snow. So it takes a while for it to compact and you can drill it. So that goes back to about 1950 or 60, and then it was only about 285 parts per million. But now it's 400 parts per million in this year 2013. We just passed 400 parts per million. It's never been that high for 5 million years, not since the Pliocene. This is why the Earth is warming. It's because we are capturing so much CO2 in the atmosphere because it's being burned, and nature, through the ocean process, can't absorb enough of that CO2 back into the oceans and get rid of it. So that's why it's increasing. And we're responsible for that. We saw what nature did. It fluctuated CO2 up to 280, once to 300, and then back down again. That's part of the warming and cooling of the glacial, interglacial cycles. We call that the Milankovitch cycles because of he's the guy who figured it out. So we are responsible for that increase above 280 to 400 parts per million. Why? Because of our population increase, the energy that population uses, and that gives rise to global warming, which results in all kinds of other things that we're not going to talk about tonight. So let's just look at human development for a moment. 150,000 years ago, well before the previous warm interglacial time, Homo sapiens were quite abundant across the surface of the Earth, in at least Euro-Asia. And about 50,000 years ago, we have behaviorally modern humans. They were anatomically modern back here, but by 50,000 years ago, they developed behaviors that are much like our own behaviors in terms of lots of things. 13,000 years ago, we have evidence at the Cooper Center that humans arrived in Orange County. They came across the Bering Land Bridge when sea level was lowered 400 feet or so, and they settled throughout the Americas. And some of the very best sites in California are right here in Orange County, Bolsa Chica and Newport Mesa. Newport is now cemented over. Bolsa Chica will soon be covered with houses. It seems to me to be kind of a pity. These are people who had a sophisticated culture that's recorded in these midden piles and village sites that we're just bulldozing. They should be national parks. It's our heritage. Agriculture came along 10,000 years ago, but we're really interested in when did industrialization and development begin. And it, of course, was linked to coal, which was burned for fuel and power, and that's the first injection of serious CO2 in the atmosphere. Although there's one guy who says we started doing that when we developed agriculture and burning fields and so forth about 10,000 years ago, and that's why this interglacial has lasted about 10,000 years instead of the 4,000 or 5,000 that the previous ones have done. And then, of course, 120 years ago, oil production began in earnest, and 100 years ago, global warming began worldwide. Took a while to get going, but now it's going faster than anybody anticipated, both in terms of the increase in CO2 in the atmosphere. We didn't expect it to hit 400 this year. It was supposed to come next year, even under a faster rate. And temperature is rising much faster than we anticipated. Let's look at this population business. Now, usually I call on my friends, but I don't know all of your names. So I'll just use myself. When I was born, there was somewhere around 2 billion people on Earth. When Darwin sailed in the Beagle, there was about 1 billion when he got back, 800,000 or something like that. 800 million, excuse me. And from that time then, the curve was very flat. We get to 2 billion. Anybody here born in 1960? So we went up 1 billion people between the time I was born in 1960. 4 billion, about 1975. Just look the way it goes. And just last year we hit 7 billion people on Earth. That's 5 billion people since I was born. That's incredible. And the same for you folks over there. Probably for you guys here, maybe what, 5 billion, 6 billion? No, 4 billion. I don't want to embarrass anybody. But the point is that the population has been increasing very, very rapidly. And although we've cut our reproductive rates in various parts of the world, we're still rising in terms of numbers of people. And there's a link between the number of people and CO2, and here it is. This shows global population, 2.8 billion out here to 6.8, and the increase in CO2 from about 315 when the world had 2.8 billion or so people, up to 380 in 2006. From 380 in 2006, we've now gone up to 400 parts per million with 7 billion people in 2013. These are linked problems. So today, if you go to the world population clock, as I did around 1230, there are 7,091,141,662 people on Earth today. Well, actually it's probably up to about 700 since lunchtime, because people are increasing, although the rates have gone down. What this projection shows is that in 2050, there will be over 9 billion people. I don't see how we can avoid that. Some of you, younger ones, will see that. Your children will see it. Your grandchildren will see it. And some of them may even see 12 billion people on Earth. It's all going to be like downtown Orange County, the world. In 2050, there will be 415 million people in the United States. In California, there will be over 50 million. When I was a kid, there was only 10. And we only had 4 freeways. Harbor, Santa Ana, Hollywood, and Pasadena Freeway. Now there are so many freeways here, you don't even call them by names. They do have names. We just call them by numbers, you know. I'll take the 5 to the 210 to the yakety yak, you know. There's just so many people out there now. And in Orange County, kind of hard to find out projections for this. There's 3.1 billion of us in Orange County this year. In 2050, maybe there will be 5.5 million people. Right now, the population density of Orange County is 3,900 people per square mile. That's more people per square mile than Bangladesh. Wow. But not as bad as some counties. I think LA has 9,000. Kids' lifetime, or your lifetimes, for you younger guys. It's going to be a different world. And here's the way it works. So every second, 4.2 people are born and 1.8 people die for a net gain of 2.4 people. That's, even though the rates may be slowing down, the birth rates, we're still gaining people. In 1 year, the world increases in population by 76.5 million people. That's the rate at which it's going. Every month, 6 million people. It's incredible. And although most of these people are not being born in the United States, we do have our own population problem. Most of them are being born in countries like China and India and other third world countries. They all have TVs and they all see what you have and they all want what you've got. That means more energy, more CO2, and that has to change too. So this is what happens with the greenhouses, the greenhouse effects. Of course, increasing CO2. Because the atmosphere warms, it can hold more water. So we see more flooding, we see more energetic weather events. Increasing El Nino events. This is the warm currents that move up the coast here instead of the cold current that comes down the coast. And it only happens every 3 to 7 years. We'll have increasing temperatures in this region of 8 to 12 degrees centigrade. You always see people arguing about the average temperature being 2 degrees centigrade. That's true for the entire Earth, but most of the Earth is tropical. It's already receiving the maximum amount of heat it can get, so the changes are in high latitudes, the big changes. So in order to balance out that territory up from 30 degrees south to 30 degrees north of the equator, some 60 degrees, the high latitudes are already experiencing extreme warming. And we'll see probably midway between there. And because of this high temperature rates in high latitudes, like Antarctica and Greenland, where there's lots of ice, and it's melting, or more likely collapsing, we'll see sea level rising to more than 8 meters. That's 27.5 feet, 8 meters. And if Antarctica and Greenland release the ice that we think that could be released, it'll be double that, 16 meters or so. All this suggests that increased hurricanes and tornadoes will occur, maybe not more frequently, but certainly increased intensity. There are 2 ways to get rid of heat. These are moving heat around in the atmosphere. And you could have more hurricanes, more tornadoes, but it looks like they're just getting more intense. Now, we just had a bunch of tornadoes, still are having a bunch of tornadoes in the eastern United States, and everybody says, oh, it's not connected to global warming. My hypothesis is that it is connected to global warming. So keep your eye out on the data. And this results in the redistribution of crops and of different species. In fact, if you're a gardener and you've kept your seed packets for a few years of the same species, you will notice that the distribution map where they will grow has been changing, and things are growing more and better in higher latitudes, more northerly in the United States than what we have seen in the past. And this is reflected in the distribution of natural organisms like butterflies, like small mammals that migrate with and that can migrate around. The medical profession says there's going to be more diseases because it's going to be warmer, and we'll see major changes in the oceans and in their biotas. The oceans will acidify because carbon dioxide, when it goes into the oceans, teams up with some hydrogen and turns it into a little bit of acid. And that seems to be affecting certain groups of organisms already, like oysters along our coast. They're trying to grow oysters now in Newport Bay, but they're being, as larval forms, killed off by changes in that. The other big change is that the oceans, as the big heat sink, will slow down, because what drives the ocean currents today at either depth or at the surface is the temperature gradient of the Earth. And if you warm the high latitudes and hold the tropics warm, that gradient declines as it gets warmer in higher latitudes. Now it's about 1 degree and about, let's say, 30. 29 difference. If it gets to be 8 or 12, it's 10 degrees and 30. So we've lost about a third of that temperature-driven sea currents, both at the surface and at depth. This means that our ocean, which should keep us cool because the currents coming down the coast from higher and more northerly places, will warm up, and we'll likely have much more sluggish currents off of Orange County. So those are the main things that we have to worry about, those three things. So this is the latest word on CO2. In February 2013, it was 396.8 parts per million, and 1 month later, it was 400 parts per million. That's the fastest rate of CO2 addition to the atmosphere ever recorded, and it's hotter than it's ever been too. This is an interesting curve, because I read in the Register the other day that temperature hasn't warmed for 16 years. And another guy in, where was that? On the internet. Well, you can't believe everything on the internet, but I can laugh about this guy. He says there's no scientific proof of global warming. What have I just been talking about? None of this is my work. I have nothing invested in it. It's all stuff that comes from the observations of scientists around the world, thousands of them. And they're not all getting grants, that's for sure. And they're not all in collusion with one another. They all work in different disciplines that focus on it. Like, I don't know the modelers very well. One I know, but that's about it. But this is an interesting one, because I do know the guy in charge of Berkeley Earth. So we have NASA's Goddard Space Flight Institute and its associated place, NOAA, and the Hadley thing Hadley Center over in the UK. And these different colors are their projections of the temperature ranges through time from 1750 to 2005. Only Berkeley goes back to 1750. The guy that leads that is Rich Muller. He's a physicist. He was he was a climate denier until a few years ago. He said that physics won't allow this to happen. He's wrong on that. Every other physicist I know says that it is a matter of physics Anyway, he said it can't happen. So he got funded by, interestingly enough, the Koch brothers. And why did they fund him? Because he was obviously an anti-climate change guy. So he ran the data. He got 36,000 different stations on the surface of the Earth in the continents. And he put it all together into a big computer thing. And this is the curve he generated. All of this stuff is, of course, before there were very many good records. You get temperature records being developed in here. And that's where most people pick it up. And you'll notice that all of these are pretty much tracking one another. And you'll notice that from about about 1980 maybe, temperature's been going like that. Richard Muller, being a good scientist but yet a conservative and an anti-climate change person, said it is warming and it's due to humans and volcanic activity. So he's a good scientist, and I know him. I had trouble talking to him before, but I think I can talk to him again. So in California, what does all this mean? Well, we're going to have increasing population, as we just discussed. We'll have a warming climate. You'll see how that works. Sea level will rise. So this is a summary of some of the things I want to talk to you about in a moment. And as sea level rises, there'll be destruction or moving of nearshore facilities, including a lot of roads, as you'll see, and these other things, El Niños and ocean acidification. We're already overfishing an awful lot, although restrictions are being imposed. But the whole biology of the oceans has been changed. Actually, not by us, by the Native Americans, because they were harvesting the heck out of the intertidal before we ever got here. So humans do that. So here's the projection for temperature in 30 years or so. And you can see this graph shows temperature change of 7.3 in these hot areas. So all of this area out there in the desert mostly will be 7.3 degrees hotter. Notice all along the coast it will remain fairly cool, and that's because of the cool California current coming down. It'll still be cooler there. And there'll still be upwelling that brings cool water from depth to the surface. But notice that in Orange County, at least away from the coast, like here and in Anaheim, it'll be a 5-degree Fahrenheit increase in most of our lifetimes. With that comes a decrease in humidity and fires. We see that happening today. They just had these 2 or 3 big fires up north of here in Los Angeles, and what did they say? The humidity is so low we can't deal with the fires. And the winds, of course. Here's something from the Register. The Register's opinion sheets, I might say, have a completely different attitude about climate change than the regular news part of the newspaper, so I like that. And here they looked at the changes in ozone, which is a way of measuring, as you know, smog, by 2050, and you'll see that here's central Los Angeles and Orange County in here. So we should have ranges in here of increased ozone and more atmospheric pollution. Another consequence. Let's just take a look at the ocean. Here's the currents. The California current comes down like this. As I said, it's a cool current. If you went swimming out here, you'd need a wetsuit. But because this gyre, as it comes past Point Conception, it's out to sea, drags warm water up along our coast, so you don't really need a wetsuit some of the time anyway along our coast. But that will change as this current slows down. Then the oceans will become warmer. There'll be less upwelling, hence less productivity in the oceans. So there won't be as many fish, many whales, or big sharks like the one they killed the other day. So here's the Pacific wide view. So you have this current coming across. Part of it goes north, part of it goes south, and that's the California current. When we have an El Nino event, when the Pacific water down here warms up and begins to move back up the coast, then we have way up here and even off San Francisco, tropical fish that normally you wouldn't find until you got down to the tip of Baja California. And we've seen that happening since the 50s. It happened even before that. Here's something that is a bit of a conjecture on my part, or a hypothesis. Most hurricanes that develop in the eastern Pacific and come up our coast go up the Gulf of California like that, and they're dissipated in monsoonal rains in Nevada and Arizona. I've experienced those out there. Terrible thunderstorms, gobs of rain falling down. But once in a while, they, especially if there's an El Nino, they don't get caught up in here. They go up here because the water's warm and this is cold. But when there's an El Nino event, this water is also warm, and the hurricanes go up sometimes on the outside, all the way to San Francisco, by which time normally they're just big thunderstorms. But here's an example of Hurricane Javier in 2004. Hurricane Javier started out down here, and this is a picture of it with its eye right there, just off the tip of Baja California. And the newscasters were predicting it was going to go up this way, and then as it got closer and closer, they argued about it. And Javier went north, outside of Baja California, as you can see here. And it came all the way up to San Francisco, not as a hurricane. We should see more of that. Some of these hurricanes might even get inside the islands offshore and whap into the coast of Orange County. So there was a time when Orange County was bigger than it is today. And that time was, as I said, here's 125,000 years. These are just geological symbols for different times. This is the 8-meter high stand of interglacial sea level. And then its sea level dropped down to 120 meters, or 396 feet, lower than it is today, just 18 to 13,000 years ago. And then it started to rise again, and it has risen up. Let me show you the shoreline of Orange County 13,000 years ago, and this is when the ice was all tied up in the northern hemisphere and more in the southern too. But this much ice required that sea level be reduced to 120 meters, and that means almost 400 feet lower. And you see there was a lot more coastal territory to build houses on 13,000 years ago than there is today. And Orange County would have gone way out here, and this continues up into Los Angeles County too. So that was all land, and that's one of the reasons we think that we don't see Native Americans these are big sites for Native Americans, Huntington Beach or Bolsa Chica, because the Native Americans were living out here, not up here, because they were all coastal at that time. So let's just take a look at ice, because we've seen what it does. It lowered sea level, and then it made it rise again until we see it where it is today. There's still a lot of ice in the world, and we've just had a big study of all the other glacial ice on the Earth. There's about 0.5 meter of sea level stored in the glaciers, like in the Himalayas, the Andes, and so on. Two big studies in Science magazine just this past week show that this is happening much faster now. So these glaciers are melting. Greenland is melting. It's got actually more than this, 7.5 or 8 meters of water stored there. The Antarctic Peninsula, mostly glaciers, 0.5 meter. West Antarctica, 8 meters, pretty much the same as Greenland. And then East Antarctica, 65 meters of water. So the total would be, if you melted all the ice on the planet, an 80-meter rise of sea level. And glaciers are melting. This is Glacier San Rafael in Chile. And I was down there in 2009, and they had painted, I had to put the numbers on here in the image, but they had numbers painted where the glacier was here. And so this is about 80 meters from there to there. And it's very rapid. They don't expect this glacier will be there in 30 more years. It's not just melting, it falls apart. So everything's calving off. And as it calves, it moves faster. Greenland also is melting. This shows 92 extent of melting, 2002. And the interesting thing about it is that all of these scenarios when it comes to ice on the continents are done as though these were ice cubes sitting on a flat table melting. They're not. They're sheets of ice on continents that are above sea level, so the ice is either going to slide off, collapse, disintegrate. Melting may be the last thing we need to worry about. One of the things about Greenland is that, of course, the Arctic basin is up here, and it's losing all of its ice. The amount of ice this past year was the least that they've seen in decades, ever, I think. And what does that do? Well, this affects the albedo. You know what albedo is? The reflectivity of the surface. So ice has a high albedo. It reflects most of the heat back. The ocean, being dark blue in the Arctic, absorbs most of the heat. So that's enhancing everything that's going on in Greenland and probably any other place around the Arctic Ocean basin, and making it happen even faster than was anticipated in models. This is Antarctica. It's 1.5 times the size of the United States. That's West Antarctica. This is East Antarctica, and there are places where you can stand in East Antarctica and look, no, in West Antarctica and look west and see East Antarctica, or something like that. Anyway, this is the part we call West Antarctica, and this is East Antarctica. East Antarctica is 13,000 feet of ice at the South Pole Station, and a little bit more in a few other places. This part of Antarctica has big ice shelves, the Ross Ice Shelf, the Ronne Ice Shelf, the Larsen Ice Shelf, Wilkins Ice Shelf, and these ice shelves are breaking up and falling apart. The Larsen has lost big chunks of it. The Wilkins is gone. When I worked in Antarctica, we sailed there, and it's gone now. Pine Island over here is gone or going, and so on. These ice sheets, ice shelves, buttress all these glaciers. When they go, then the glaciers start moving faster. And then we start losing the ice up here. So that's what I mean by disintegration of the ice in Antarctica. If West Antarctica goes, all of this, that's equivalent to 8 meters, or about what we get at Greenland. This is the SubIce topography. Everything in blue is below sea level. And you'll notice that most of the West Antarctic ice shelf, all this stuff, is below sea level where it rests. This means that it's quite possible that this could be filled in with water, seawater, because it's below sea level. And then that would increase the rate at which these ice masses disintegrate. The way these things fall apart is chaotic. We can't really predict them. In fact, the last IPCC report in 2007 said that sea level will rise 1.4 meters due to the thermal expansion of the oceans as it warms up. But we can't predict the ice because it's too chaotic, so we're not going to say anything about it. To me, that's like sticking your head in the sand, but it's good science. But they should have said something. We know that the ice sheets will disintegrate one of these days. We just don't know when. Because that would have been a more truthful statement. Then we could have planned something about it. So here's the people in California that will be impacted by rises in sea level. Let's take a look at some of these. There's 2,100 when the IPCC predicted that we would have a sea level rise of 1.4 meters, or about 5 feet. 440,000 people will be impacted by that little bit. And of course, people say, well, that's going to happen in 2100. We don't have to worry about it. Well, we got to worry about at least half of it by 2050. And that's where that'll be. And that'll affect 224,000 people. And then 1 million people would be affected if it got to 10 feet. And they predict that would be 2150. None of these figures include the catastrophic collapse of ice shelves, which could happen. Most of the ice people refuse to put figures on it. Some say you can't really collapse it and let it slide off of the continent because of the topography. It's too rough. Others say that it's easy enough to do. So there are a lot of questions about it, and it's being studied, in fact, by a guy over here at UC Irvine. So what does a 5-foot increase in sea level do to Orange County? The Pacific Institute up in Oakland looked at the entire coast of California, and they published this showing these areas as inundated by this 1.4 meter rise in sea level just due to thermal expansion. And you can see that up here in Huntington Beach and that area, that there will be big incursions of the ocean. In fact, we even have that happening nowadays with these big tides. What do they call them? King tides. Remember last winter they washed across the Pacific Coast Highway. So we know what happens there. And here's the impact caused by this rise in sea level. In Orange County, which is the third most impacted county in the state of California, Los Angeles isn't as impacted. You see there's 540 miles of highway in Orange County that will be impacted by just 1.5 meters rise in sea level. The other two counties, I think, are Alameda County and San Mateo County in the Bay Area. That'll be $17 billion of repairs or realignments of just the road infrastructure. There's a lot of other things it's going to affect, say nothing about housing and electrical systems and everything else. This is just roads. Here's Dana Point. This originally was just a point, and it came around like that, high cliffs. And then they decided that they'd build a marina. And if you've been down there, you can stand anywhere here on this marina and you're less than 5 feet from the ocean. This will be gone. Here's Newport Bay. There was an article in Orange Coast magazine about what this 1.5 meter sea level rise will do to Balboa Island. It would be flooded. So they are planning, according to the magazine, on building 5 or 6 foot dikes all the way around it. So now they'll be living in a hole in the ocean because this beach here, the maximum elevation in this area is 10 feet. Most of it's around 5 or less. So there will be ocean, if they could see it, they'd have an ocean view all the way to Catalina. Same with Lido Island and the other places. Also, there'll be flooding all the way back through upper Newport Bay. And as far as this goes back there, I'm not quite sure of the topography back there, but there'll be flooding here. But these cliffs are about 100 feet on either side, so it'll just be a big, deep lagoon instead of a marsh. And of course, this extends up the coast too. So all of these beaches will be severely impacted. I see where San Clemente is investing $20 million, was it, to put more sand on their beaches? It's just going to keep rising, and what rising sea loves to do is tear the beaches up and deposit that sand offshore. Maybe they have something better to do with their 20 million. This is upper Newport Bay, where I've worked. This is about 100 feet high, that cliff over there. So let's see what 5 meters would, or 5 feet would do. There's where it would come with 5 feet. If we melt Greenland or West Antarctica, it'd be about 1/3 of the way up that hill. And you see that they're already having problems there. If we can back up, because they've got big plastic sheets draped down over the places where the cliffs are failing already. But that'd be pretty nice to have a house up there and look at all that water. Probably a lot of fish, stuff like that. So global warming isn't all bad. Here's what it would be like, roughly, from LA Harbor, this is LA Harbor, all the way down to Newport. This is with a 27-foot, that's 8 meters, roughly. I mean, there are places where it'll go back farther that are not included on here. And here, this will go much farther back. So Orange County, although we had a lot more land 13,000 years ago, in another few tens of years, it's going to be a lot less. And this is what would happen if both West Antarctica and Greenland lost their ice into the ocean. Then all of this territory would be inundated. Now, you wonder, what's going on with our governments? Well, it turns out our governments are doing all kinds of things. California has programs to try to deal with rising sea levels. They've done extensive studies. They've done engineering studies, policy decisions of what to do. And individual cities along the way have done that. The entire Bay Area had a big contest where they said design some way to 2.5 or 5 feet rise in sea level in the San Francisco Bay. And they had a contest. They had a bunch of entries, and they selected 4. They gave $10,000 was the prize. So all these engineering firms, they drew up their plans and they awarded 4 different ones. Each engineering firm got $2,500. So they're worried about it and they're planning for it. You ought to ask your own city if you live in a coastal community like Newport Beach, which wouldn't even be there. And of course, this is going to be happening worldwide. Every place in California, every place in the United States that's coastal will have to deal with this. And so we're going to be one small county screaming for help when everybody else is screaming for help too, including Manhattan and New York and Miami and Houston. And you go around all the coast, San Francisco, Seattle, Newport News, Virginia, San Diego. They're all going to be needing a lot of help. Well, when is this going to happen? We've seen that the natural variations take on the order of thousands of years. We can change things in less than 100 years by burning fuel, and maybe in tens of years through the sudden releases of methane ices buried in the sea floor. We see that happening today. Or the catastrophic collapse of ice sheets. We could change the entire climatic system and sea level within a couple of decades. So if we have that happening, it could be happening at a rate that we couldn't deal with. We'd just have to migrate away from the sea, most likely. So in your kid's lifetime, we've talked a bit about this, the population will increase from 7 billion to 9 or 10. US will increase by 50 million, excuse me. Petroleum will be used up. I don't think fracking is the greatest thing I ever heard about, not just because of the environmental impact. It's just not as efficient as the estimates. They're talking about fracking the Monterey Formation here in California, and the companies that are already out in the field doing that claim that there's 300 billion barrels of oil that they will retrieve from the Monterey Formation. Those people who aren't in the field say it's 15 billion, but the Monterey is fractured and folded, and it's not like the places where they're fracking now. They may not have much success with that. So we'll see. The editorials in the Register seem to think that this will save California with 250,000 jobs and billions of dollars. I wonder. So do other geologists that have worked with the Monterey Formation. Sea level will go up, climate will change, and all these other things will happen. I don't think that looks very good for our kids. I think we need to do something now, just as you would do if you were driving a car, or if you lived in tornado country, you'd build yourself a place to hide from those. Or the same with hurricanes, or Crescent City, where they get hit by tsunamis every once in a while. They've cleared the ocean front so that there's nothing to knock down. They've planned for a tsunami, even though they don't know when it's coming. We're not doing that planning very well publicly. I think NASA, not NASA, but NOAA, state agencies, federal agencies, they're all planning for this stuff. Even the energy sector is planning for it. While they stand in front of their stockholders and say, as the CEO of Exxon did last week, if we fail to produce oil, it'll be a disaster for humanity. Well, it'll be a disaster for humanity if you do it. So some people tried to vote him down, but the stockholders voted for him. On the other hand, those companies are already planning to drill the Arctic Ocean when the ice is all gone, and they're planning to use the Northwest Passage to get that oil out of the, and they've got some of the finest geoscientists there are with the biggest computers that you can imagine. And they're already planning on global warming, even though it doesn't come to the fruition of the business side of the company. Instead, they give a few $1 million to people like the Heartland Institute, who then make a bunch of other claims. So I think only we can do something about this, and we can do that in a number of different ways. Because you're already being impacted. All of these different things are happening to us already. This one is an interesting one. I have the map, but I don't want to show it to you just because I don't know anything about allergies. So here's some of the comments and questions you're likely to hear from people out there as I've been hearing these. These actually came out of I did an OLLI course for UC Irvine, and I talked about, it was about astrobiology, and so I was talking about CO2 in the atmospheres of those planets. And so they asked a bunch of questions, and with statements, not questions. They told me that volcanoes release far more CO2 than human activities do. There are times when that's true, but not today. Cold winter storms show that warming is not happening. Well, you got to remember, climate is not the weather. The way I like to think about it is if you put a pot of boiling water on the stove burner is the climate, and the water in the pot is adjusting to that heat that's coming from the bottom. And it's turbulent because it's trying to move the heat around, and that's what the atmosphere does. It's moving heat around. So the greater the heat extremes are, the more energy we'll be dealing with. And also, the cold winter storms are bringing a lot more snow because there's more water in the atmosphere. Some people say the CO2 increase is too small to be important. That's just a misstatement of physics. One guy said, well, you breathe out CO2. Yeah, I do. We all do. And the plants breathe it in. And it has no effect on climate. That's because it's pretty much in balance. Plants use up CO2. That's true. And you know, a lot of organizations say plant a tree, save the atmosphere. That's true. It's a temporary storage of CO2. But as soon as you burn that tree or it falls down or the leaves fall off, the CO2 goes back into the atmosphere. So other people say scientists exaggerate the problem. And I haven't tried to exaggerate the problem. Today I have emphasized certain points that I think are important to us in Orange County, or that are important to our children and our grandchildren, more importantly. They said Al Gore's a fraud. Well, Al Gore was just a messenger. Well, I heard him talking on the internet today about it. And then just the other day in the Titan newspaper, some business professor said climate change is a hoax. Now, you can say I've hoaxed you today, but that's not the truth. I have presented a bunch of data here that I have no vested interest in, but I don't believe it. I accept it. And if anybody can disprove any of this that I've just given you, then I will change my views. So I'm not a believer in this stuff. I just accept it because that's the way it seems to be. So what about this? That's nothing to worry about, they tell me. I think you should worry about it. And ice will not be a factor until long after 2100. I wonder who they're talking to. It's certainly not the scientists I know. And then what about nuclear power? Well, I'll let the San Onofre fiasco speak for itself. Some people say we just have to get away from the really large nuclear plants and start using smaller ones. So, in order to avoid these impacts on OC, we need to call the climate change deniers what they are. They're wrong. They're selective, they cherry pick, they push things in their own directions. They fool the public into thinking that there's no problem. There is a big problem, and it's happening today. We see it happening. And so they hinder progress to limit CO2 in the future. That's one way out. And of course, the politicians, they fail to enact any legislation, but climate change they're not likely to do very much with. And all of this debate detracts from the local preparations that we could be doing, and the financial resources are not going to where they're needed. This is a survey of almost 14,000 peer-reviewed climate change articles published from 1991 to 2012. Only 24 of those rejected global warming. Now, that's an awful lot of scientific coherence. I don't think that this is a big fraud. It's certainly not a hoax. The climate hoax is a hoax. The climate hoaxers are a hoax. This shows the increase of energy-related CO2 emissions, and it's, as I showed you before, increasing quite rapidly. This is in gigatons, not parts per million, but it's the same. And here's part of the problem. We have scientists like those I showed you before. Some of them have a high, their curves are higher because of higher emissions, others are lower. And the point of this is that if you can decrease the emissions down to lower ones, you decrease the amount of heat and decrease the amount of CO2 in the atmosphere in particular. So that's something we could do. But we'd all have to say we're not going to drive our cars anymore, at least if they burn. I'm not sure I want to do that yet. So here's the 10 things you can do right now. Question those deniers. Ask them the hard stuff. And tell your friends about this problem. Tell your kids, tell your grandkids about it. Use Facebook and Twitter. That seems to be pretty effective. And then learn more about the problem so you can talk about it. And maybe volunteer to help in some of the organizations that are around here, like the climate change group from Orange County, right? So you can do that. You could join those groups to help solve these climate problems. And I think really importantly, we have to work through our national government and through local governments as well, by writing to policymakers, getting involved, and then individually you can cut your carbon footprint. And then 10, I have a little despair here. Promote alternative energy sources carefully. I added the carefully because I don't think that this is very attractive. I think they've destroyed the desert. I have my value in nature. And windmills, the way they did it here out there by Moronga, is just a disaster as far as I'm concerned. And they're only pumping electricity for 300,000 houses. That's a good number, but I don't know. We're getting windmills all over California.
They're just ugly, or is it?
Well, they are what?
Are they just ugly to you, or is there something else wrong with them?
Well, they destroy the desert. I don't know. It just rubs me the wrong way. My value is in nature. This is not nature. But I may have to accept it. So I showed you a slide of it. It's probably better than nuclear power plants cracking up. Well, thanks very much. You can go to this website. The Environmental Protection Agency has a individual calculator for carbon footprints, and you can calculate your own. If you don't want to mess with the government, the Nature Conservancy, they have one. Just Google climate footprint and you'll get a calculator, and you can figure out exactly how much you're contributing. And I know that I contribute, what was it? 8 tons driving my car, and my friend with a Prius contributed 2. So I'm guilty. Thank you very much.